All right, I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and just ask you to guide our steps today, help us to glorify you what we do, and just understand what we need to prepare for the third test, Lord. In your name I pray, Lord Jesus. Amen. All right, well, this is very stupid, but here we go. Let's see here. All right, so this is the solution to the homework, which I wanted you to have done today, but obviously something got miscommunicated. If I can find my laser. Let's see here. Well, all right. So find the direction of the induced current as the loop enters the region. So as the loop enters the region, the magnetic field coming out of the page at you. So it's increasing, right? So to decrease the amount of flux going out of the page through the loop, we want the induced current to go the other way, so clockwise. Now, part B, if it's all in the loop, the induced current 0. Part C, because it's not changing, right? If the flux is not changing, then of course the induced current is 0. And when it's leaving, let's see here, as it's leaving, the flux going out of the page is decreasing, right? So you want the induced current to be in such a direction as to it increasing that flux, so that's why you want a counterclockwise induced current in that case. So these are all Lenz's law, right? All right. For problem 34 here, we've got some region in the plane. I give you the formula for the magnetic field component that's perpendicular to the plane and some values. So basically we just do B times A because the direction of the field is the same as the direction of the area everywhere. So it gives me A alpha sine KT. When I differentiate, that gives me the induced voltage, which, yeah. So that gives me that the current is that divided by R. So if you want to put numbers in, which isn't particularly interesting, but you can, it's that. So there's the induced current. So this is just straight, what is this, straight Faraday's law, right? Time rate, the derivative of the flux is equal to the induced voltage. And then Ohm's law gives us that the voltage is the current times the resistance, right? So that's that. This is the usual sliding bar problem. You've got a magnetic field that's coming out at you of 2.5 Tesla magnetic field perpendicularly downward into the paper. So as this slides that way, let's see here, as it slides that way, you're increasing the flux into the page, right? So the induced current wants to oppose that increase, and so it wants to make a flux that goes out of the page. So you want a what's that? Counterclockwise current. In any event, the magnitude of that current is given by the derivative of the flux with respect to time. Oh man, this thing's bright. Which ends up giving me A is x times L, right? So the L is constant, so you got BL. Wouldn't it be interesting if the rails were like triangular instead of like parallel? Wouldn't that be more interesting? Go like that. Then the L would be a function of time, just like x. What if they were wiggly? Okay, anyway, I digress. So that gives us bliv which then, again, I times R, so is the voltage, so I get I as BLV over R. Now the force on the wire is directed leftward, right? Because as I was telling you, the induced current goes counterclockwise. So the force, the induced current's going up like this. The magnetic field's going in. So I, if I can do it eventually, I crossed into B like that, right? So the force on the induced current is leftward. So you have to push against that to keep it going out, right? The bar would naturally stop itself if there was nothing else to keep it keep moving it. Notice that it's going at a constant speed, right? So that shows you that the net force on the bar has to be 0, right? So there's two forces that are in play. The one is the the Lorentz force, the current ILB force, and the other is just whatever dude's pushing on the bar to make it go over, right? Which is not pictured. But anyway, the sum of the forces must be 0, which means the pushing force or the applied force must be BL squared V divided by R. And sorry, all these problems have like really boring cross products. I'll find one that's more interesting for the test, don't worry. Because like you do need to know cross products. They're not always perpendicular, you know. It doesn't have to always work out like that, but it seems to keep working out that way for these problems. B squared L squared V divided by that. So you got your 2.74 newtons. And let's see, what else happens? Well, what rate is the energy delivered in the resistor? Well, I squared R, right? But check it out, I squared R here is actually also equal to the force times the velocity, which makes a lot of sense, right? Because power is force times velocity. Assuming it's average, the force is constant, in this case it is. Anyway, 5.157 watts, that is joules per second. Given diagrams below, direction of current in each case. So if you're pulling the loop down, the flux into the page is decreasing as the loop moves down, which means the induced current should increase the downward flux, which means that we're talking about a clockwise induced current, right? To increase the flux downward to stop its decrease. This one, we're pushing the loop up in, and so as we push it up in, the flux is increasing out of the page, right? So we would like the induced current to decrease the upward flux, which is to say to increase the downward flux. So again, clockwise, A and B both clockwise. All right. And then, let's see here. Solenoid length 20 centimeters. We got here 6 amps flowing through it, 20 centimeters. We're given that the magnitude of the magnetic field close to the middle of the solenoid is 0.0188 Teslas. What's N? So you guys remember, we've worked this out before. You should be able to derive that formula for the test, right? That's often a question I might ask in test 3. Derive the formula, mu naught Ni. How did we do that? Search your heart. Find how we did it. Better yet, look at your notes. But what am I saying? Physics is all about feelings. You need to follow your heart. And that's pretty much always bad advice. But the heart is desperately wicked above all things. Who can know it? It's Jeremiah 17:9. Does cast a long shadow over psychology, I think. But anyway, N is equal to the total number divided by L. That's the turn density, right? Now we don't know big N, but we do know L. So if we put that in, we've got the magnetic field as mu naught big N I over L. The only thing we don't know here is big N, so solve for it. And you do that, and you get that, 498.7, I believe. So, yep. Now if you put down 499, I'd still count it right. So. These problems, I almost always ask a question like this on the next test because they're just nice. So here we have an RL circuit. We're supposed to suppose the switch is closed. Oh, I'm sorry. I was thinking of a different problem. This problem I don't always ask. But this is also nice. There's a lot in here. So as we close the switch, right, once we close that switch, right, there's immediately 30 volts across the 30 ohm resistor, right? So it's the moment that switch closes, there's 1 amp flowing through the 30 ohm to the far side of the circuit here. So you got 30 volts over 30 ohms, 1 amp flowing over there. Now originally there's 0 amps flowing through the middle branch, right? Because initially the inductor behaves like an open circuit. So anyway, we have to solve the differential equation. On the one hand, we have Kirchhoff's current law, or if you like, conservation of charge at the upper node. Boop. I is equal to I2 plus I3. That's true. On the other hand, if we follow the Kirchhoff's voltage law around the loop, we get the voltage minus I2 times R, which is 15 ohms, minus L di2 dt equal to 0. There seems to be a 0 missing from this equation. Sorry about that. Yeah, it's just not. No, I upgraded it to an equation in the next step, so that's good. So this hanging expression implies this equation. There just needs to be a 0 here, okay? There's a 0 equals to that, but the 0 and the equals is in white, so that's why you can't see it. So sorry about that. Anyway, so we have di2 dt is equal to plus r over L times I2 is equal to E over L. We've solved this before, integrating factor method, or separation variables even, we'll do it, right? Anyway, we get C1 e to the minus t over tau plus E over R, where tau is equal to L over R. And this time, the current is 0 at time 0 in this one. So that forces the constant to be minus E over R, which gives me this lovely formula. I2 is equal to all this jazz right here, right? But going back to I, remember I was what? I was I2 plus I3, right? But I3 is always 1. So I do 1 plus E over R. This is 30 over 15, which is 2. So I get 2. And then I've got 1 minus. And apparently R over L is 5,000 in this context over seconds. And so there you go. This one is not a bad test question in some sense, because it's kind of between the most draconian problem that we worked, the parallel inductor problem, right? Versus what? Like the series inductor problems, kind of, this is kind of on the same tier of difficulty as the series inductor problem. Yeah.
Are you particular about how we solve the differential equation?
I just like them to be solved correctly. Yeah. So, I mean, can you memorize the solution to a particular first order differential equation and just use it? Yeah, you could do that. But do it correctly.
No, I'm asking about different solution processes.
Well, you could use integrating factor method. You could use separation of variables. If you got Laplace transforms, you can use them.
Not yet.
So, I mean, whatever you think is best. Obviously, like your own solutions, copying, phones. Yeah. Sorry. Now this one here, find the currents and voltages, assume the circuit's been connected for a long time. So in that case, the capacitor is like an open circuit, right? After a long time, the capacitor is totally charged up. No current flows through there. After a long time, the inductor here, right, is like a short circuit. So no voltage is dropped there, right? So essentially, it's like this. And I guess I could, well, anyway, this is an equivalent circuit. So what's the current? It's just E over R, right? The total current, I1 is E over R. And the current that goes through 2 is also E over R, because no current goes through R actually, because all of the current goes through the inductor for long times. So no voltage is dropped across here at infinite time. I3 is also 0 because after a long time the capacitor is like an open circuit, as we've talked about. And V1 would be the whole voltage, because again, this inductor is like a short circuit, right? So no voltage is dropped across a short circuit. That means that essentially the top of the voltage source and V1 are effectively like the same point. Of course, that's not actually true. They're physically different points, right? But they're at the same voltage because no voltage is dropped across the inductor in this situation at infinite time. So anyway, there you go. Jump in if you got questions. We talked about these last time, I think, so I won't belabor them. But you know, the integral form, you could, I guess you could. I have no. The differential forms, they are what they are. All right. The integral forms, you might say something slightly different, and it would still be correct, possibly, I suppose. But you know, we have Gauss's law, the no magnetic monopoles law, Ampere's law with Maxwell's correction, and then of course Faraday's law. These together are the story of electromagnetism. These are Maxwell's equations, discovered about the time of the War of Northern Aggression. Oh, I'm sorry, Civil War. Civil War. What's wrong with me? I mean, I was born in upstate New York, so Lincoln's a great guy. What's that?
Where in upstate New York? Where's wrong?
Vestal.
Where?
Vestal. Where? Oh, okay, that's really upstate New York. Yeah, I'm like southern tier. So, it's almost Pennsylvania, really. Yeah. So, conservation of charge. I worked this out in the problem session, so you can watch me blather on about it there. I don't want to talk about it here so much. With that, let's go back and what was the last mission we had? Was it mission 5? Got that in here somewhere. What's that? Well, if it hasn't, that's unfortunate. Did I not post a solution to mission 5? What? Why don't you guys ask me about these things? You ought to ask me about these things. You accepted my eccentricities? I like that. Well, I guess I'll put a solution together for you guys and post it a little bit later then. Any questions? So my apologies, the mission's not back yet. Obviously, no. Huh. Well, that's odd.
May I suggest?
Yeah, sure.
You could switch, well, just switch Friday and Wednesdays, as in you did. Make the mission do it.
Oh, no, I think test 3 is Wednesday. It has been Wednesday. It's staying Wednesday. Yeah. Let's see here. Where was that? I feel like, I mean, I have solved mission 5, I know, because I gave a solution to the grader with your homework, with your work. And I guess the grader has just been busy.
I believe you walked through it. You may just not posted it.
So I don't. I've definitely solved mission 5. Anyway, I will find the solution to mission 5 and have it posted here for too long. Let us talk about what is on the test then. So what would be on this? So first of all, I have talked about old test 3s in the problem session at length. We've looked at like, I don't know, 3 or 4 different versions of test 3 from yesteryear, you know, so you can glance over those if you like. For us in here, I would expect that there's probably like, you know, we spent a fair amount of time on the Biot-Savart law and working out how to integrate the Biot-Savart law to find the magnetic field. So I wouldn't be too surprised if there's a problem like that. I almost always ask a question about like a long line of current and like finding the magnetic field at some point off the, you know, off somewhere. What's its magnitude and direction? Or sometimes I ask for a pair occurrence, something like that. The force of attraction or repulsion per unit length for a pair of parallel currents, that's always an interesting problem. The sliding bar problem is always interesting. There's a lot of different versions of that. Find the voltage in a loop if we drag it away from a current, right? What's the induced voltage if we drag a square loop away from a current? Or if we drag a triangular loop away from a current, how's that go? Let's see here, what else have we done? Obviously the, equivalent inductance, we've derived those, so I could ask a friendly, easy question about that, or I could ask you to derive them in principle. Although I will say if I do ask you to derive the parallel inductance problem, then that's like half the test, RLC circuits, we didn't go too deep into because I haven't really fully solved the second order differential equation. So there you're mostly responsible for the LC circuit, where we know the full solution for. It's good to understand conservation of energy there. We worked that out in class. Electromagnetic waves, we don't have too much to work with there, except that we can talk about the general features that I talked about last class. As I told you guys in the problem session, there are some old problems on the old test where I give you the electric field and ask you to find the magnetic field. I specifically ruled those out because we haven't had enough examples of those. Perhaps I'll talk about those Friday, so that it's fair game later. But yes, that's pretty much it. So it covers chapters 27 through 32. In terms of recommended homework problems in those chapters, I would refer you to the problem sessions where we have worked a selection of these there. So let me see here. Let's see here. Module. See, like this is in Canvas, right here. This is at the start of the module in the introductions I'm required to write. And it says plain as day here, mission 6 due, right here. Now I understand the Canvas calendar apparently doesn't have this, and that's unfortunate, but like it has been here the whole time, and I'll get over it eventually. Any questions about the test? So what are the main laws we're testing? Ampere's law, right? Faraday's law. And what's the other one? There's really two others, I think. There's the Lorentz force law, right? And the Biot-Savart law, right? Those are the four big ones, I suppose. So there's another thing don't forget to have on your list of formulas. The pointing vector, what's that? You guys are allowed what, a 3x5 card or?
Yeah, 3x5.
3x5 card, okay, that's good. Presentations. I should make you guys give presentations. Why don't we have presentations in here? I'm working too hard in here. I should make you guys do presentations. I'm gonna start that next year. I have what? So the pointing vector is what? It's 1 over, what was it? 1 over mu naught E cross B, I think. Is that right? I hope it's right. Yeah. So the significance of that, of course, is it points in the direction in which an electromagnetic wave with electric fields E and B is waving, right? So E cross B points in the direction of the electromagnetic wave traveling. We did talk about that. So that's one kind of question I could give you. I could say like, here's the electric field, here's the magnetic field, here's a point charge with a certain velocity. What's the force on the point charge, right? How would you figure out the force? You do what? QE plus V cross B, right? That would be the force on the point charge with velocity V. What's that? QE, yeah, QE plus QV cross B, thank you. And then the direction in which the electromagnetic wave that was in question there was going would be the cross product of E and B, right? That's the pointing vector. Other questions? Not really been a question yet, but. I'd say the other thing that comes to mind, of course, is like, can you solve the charging capacitor? Can you, or the discharging? Wait a minute, is that? Hold on a second here. We already did that. We did that already. Asked and answered. All right. Let's see here. Let's stay on task. So the charging inductor is what we're talking about in this test. You know. I think you understand that pretty much everything we talked about circuits-wise is still very much on the table, right? Because all of that's needed to understand these long-term steady-state problems, I think. But, yeah. In any event, I hope that gives you a good idea. I'll let you guys go. Unless there's another question, I don't see any point in continuing. I will try to have the solution to mission 5 posted sometime soon, guys. Sorry about that.